Welcome back to the deep dive. We're doing something a little different today. Usually we take a topic, maybe it's a historical event or a tech trend, and we peel back the layers.
Right.
But today we are stepping into a simulation. We're putting on the lab coats, adjusting the goggles, and entering the high-stakes world of competitive forensic science.
That's right. We're looking at a science Olympiad event with arguably the best pun in the entire academic catalog, Sherlock Foams.
It's a fantastic name. I mean, it sounds like a bubble bath detective agency. But the reality is so much more intense.
Oh, absolutely.
We've pulled this massive stack of training guides, rule books, lecture notes, all the cheat sheets for this event. And what I really love is that this isn't just a game of Clue. It's not just guessing who did it.
No, it is a rigorous test. It's deceptive, really. You walk in, it looks like a board game. You have suspects, a crime scene, evidence bags. But to actually solve the puzzle, you can't just guess.
You need the science.
Exactly. You have to understand ionic lattices, antigen-antibody reactions, fluid dynamics. You have to be a scientist first and a detective second.
And that's our mission today for you, the listener. We are going to decode the science behind the clues. We've got a lot of ground to cover because this event is basically a crash course in everything a forensic lab does.
It really is.
We're going to break down the white power problem, how to identify mystery substances that all look identical. We are going to sniff out the truth with liquid analysis, safely, of course.
Definitely safely. And we'll watch ink molecules race each other in paper chromatography, which is just a fascinating look at molecular polarity.
Yeah, we're going to decode the friction ridge patterns on your fingertips and unpack the life or death compatibility of blood typing.
And finally, we'll talk about how to synthesize all that data into a legal argument. Because being right isn't enough. You have to prove it.
You have to write the analysis that puts the bad guy away or clears the innocent name.
That's the key. Observation, pattern recognition, knowing your chemical reactions, building a narrative that stands up to scrutiny.
So settle in. Whether you're a science geek, a true crime fan, or just someone who wants to know why cornstarch acts so weird, let's unpack this case.
Let's do it.
Okay, so before we even touch a test tube, we have to talk about the environment, the lab. If you walk into this event or into a real FBI forensic lab, what is the immediate non-negotiable vibe?
It's controlled chaos. But the controlled part is heavy on the safety regulations. The first thing you notice is the fashion. Or really the mandatory lack of fashion.
Right.
In Sherlock Foams, safety gear isn't a suggestion. It is the entry ticket. If you don't have it, you just don't compete. We're talking ANSI standard goggles.
And we need to be really clear here. Not resting on the forehead like cool aviators.
No,
not hanging around the neck.
Sealed over the eyes. If you are in the lab zone, the eyes are covered. And the clothing rules are incredibly strict. The source material emphasizes this repeatedly. Long sleeves, long pants. There is a very specific hard ban on shorts.
I found that so interesting in the notes. Why the specific hatred for shorts? Is it just a professional aesthetic thing?
It's entirely a skin contact risk assessment. Think about what we are handling. We have hydrochloric acid, we have iodine stains, hazardous biological simulants. If you spill a beaker of acid, gravity takes it down. If you're wearing shorts, that acid splashes directly onto your bare shin.
Ouch. Yeah, that makes sense.
Chemical burns are nasty. They aren't like heat burns where you pull away and it stops. The chemical keeps reacting with your skin until you wash it off.
Right. It just keeps burning.
Exactly. But if you have long pants, ideally baggy ones, that fabric acts as the first line of defense. It absorbs the splash, giving you those crucial seconds to get to a safety shower or strip the clothing off.
The notes actually mention that tight clothing is discouraged too, like leggings or skinny jeans, which is interesting because that's what a lot of people wear to be comfortable.
Yes, and for the exact same reason. If a chemical soaks through tight yoga pants, the fabric holds that corrosive substance directly against your skin, like a poultice.
Oh, that's terrible.
It accelerates the burn. You want air gaps, you want layers, you want to look like you're ready to paint a house.
Dress like you're going to a hazmat party. Got it. Now, one thing that stood out to me in the rules, and this gave me flashbacks to my mother yelling at me, was the cleanup.
Oh, yeah.
Cleaning your station isn't just polite here. It's a massive part of the score.
It is huge. It's the place where Ricky teams lose the gold medal. The rules state that if you leave your station a mess, powders spilled, beakers dirty, pH strips left on the counter, you get points docked. Significant points.
Disqualified in some cases, right, for being messy. That feels harsh.
It feels harsh, but think about the context of forensic science. Contamination is the enemy of truth.
Okay, fair.
If you leave a pile of baking soda on the table and the next team comes in and sets their evidence down in it, you have corrupted the chain of custody. You've ruined the experiment for them.
Enforcing lab discipline. It's about preserving the integrity of the data.
Precisely. The sources highlight a 2-minute warning. When that clock is ticking down, usually it's a 50-minute event, you have to make a hard tactical switch.
You have to stop solving the crime.
You stop analyzing, and you start scrubbing.
It adds this crazy layer of time management pressure.
It does. Imagine you're on the verge of identifying the killer, but the proctor yells 2 minutes. You have to drop the pencil and grab the paper towels, because the penalty can be up to a 50% reduction in score for a safety violation.
That is wild. You could solve the murder perfectly, write a beautiful report, but fail because you left a dirty pipette on the table.
It reflects reality. A messy scientist is a bad scientist. If a real forensic lab is messy, their results are inadmissible in court.
Speaking of not being a bad scientist, let's talk about a specific technique mentioned in the safety protocols, the art of wafting.
Ah, yes, the waft.
This is one of those things you vaguely remember from middle school science, but the sources get really specific about the why. You have a mystery liquid, you need to know what it smells like. The human instinct is to stick your nose right over the vial and inhale deeply.
Which, according to our notes, is a catastrophic idea.
Yeah.
Especially when one of the potential liquids is ammonia.
We'll get into the chemistry of ammonia later, but the description of the smell in the source material is visceral. It described it as feeling like it's buzzing or going straight to your brain.
That's a very accurate description. Ammonia is a strong base. It's a pH of around 11 or 12. When you inhale those concentrated vapors directly, it's not just a smell.
It's physical pain.
It's a chemical attack on your mucous membranes. It shocks the respiratory system. If you take a direct hit, your eyes water, your throat closes up, you are out of commission for a few minutes.
So the technique is wafting. Walk us through the proper form here. It's not just waving your hand randomly.
No, it's almost a dance move. You hold the container a good 6 to 8 inches away from your face. You do not lean in, keep your head back. Then you use your free hand to fan the air above the container toward your nose.
Like you're trying to cool down a spoonful of soup, but in reverse.
Exactly. You are gently pushing a small amount of vapor toward your olfactory sensors. You get a diluted version of the scent. Enough to say, oh, that's cleaning fluid, without burning your nostrils off.
It's like a polite wave to the chemicals. Hello, what are you? Instead of a bear hug.
That's a great way to put it. You have to respect the chemistry.
Okay, so we're safe, we're wafting, our goggles are on. Now we turn our attention to the table. We are presented with a classic forensic puzzle, the white powders.
The bane of every new chemistry student. You look at the table, and you have 5 or 6 piles of white dust. To the naked eye, they all look roughly the same.
But they aren't. And this is where we get to identify them using observation and chemical reactions. Let's start with the basics, the stuff we put on our fries. Salt.
Sodium chloride. Now, if you just glance at it, it's white powder. But if you look closely, maybe with the hand lens provided in the kit, salt has a very distinct geometry.
The crystal structure.
Right. It forms a cubic lattice structure. The grains are usually square or cubic blocks. They're non-regular, meaning they aren't all perfectly manufactured identical cubes, but they have that blocky, sharp-edged structure, like little shattered blocks of glass.
And chemically, how does it behave in the test?
Honestly, it's boring.
Boring.
In the context of this test, yes. It's chemically stable, unreactive. You drop iodine on it, it just turns the orange-brown color of the iodine. You drop hydrochloric acid on it, nothing. Vinegar, nothing. It just sits there.
So if it does nothing, it's salt.
Or sugar. But we'll get to that distinction. Salt does dissolve in water, obviously. And here's a fun bit of trivia from the notes that might show up on the written portion. The human body contains about 250 grams of salt.
That seems like a lot.
It's essential. It regulates fluid balance and is critical for nerve signals. Your neurons are firing using sodium and potassium pumps. So if the victim was a marathon runner who collapsed, salt levels might be a relevant context clue.
Okay, so salt is the blocky, boring one. Now, you mentioned sugar. How do we tell sugar apart from salt if they both just sit there and ignore the acid?
Visually, sugar sucrose looks different under the lens. The grains are more irregular, often described as tortured crystals. And they tend to be slightly translucent or clear compared to the opaque white of salt.
And it dissolves in water.
Yes. The real tell is often the context combined with that crystal shape. And organically, it's a fuel source. The source material had some Wild trivia for sugar, too. Apparently, the first sugar refinery was built in Venice in the 15th century.
Venice, the city of canals and sugar.
And get this, sugar doesn't spoil. Bacteria need moisture to grow, and sugar is hygroscopic. It sucks water out of bacteria, killing them. You could theoretically eat 500-year-old sugar if it was stored perfectly dry.
I think I'll pass on the vintage sugar, but good to know. Let's move to the stuff that actually does something interesting, the starches.
This is where we bring out the heavy hitter of forensic chemistry, the iodine test.
This is the magic trick of the event. It looks like alchemy.
It really does. Iodine solution is naturally a brownish-yellow, rusty color, but when it meets starch, it turns this deep, dark blue or midnight black instantly.
Why does it do that? Are they swapping atoms?
Actually, no, it's a physical interaction, which is cooler. Starch is made of two types of molecules, amylopectin and amylose. The amylose molecule is shaped like a helix, a spiral staircase.
Okay, a spiral.
The iodine ions, specifically triiodide ions, are linear. They fit inside that helix like a sword in a sheath. When they get trapped inside that spiral, they interact with light differently. The complex absorbs almost all visible light.
That is fascinating. It's not changing the molecule, it's just hiding inside it and blocking the light?
Yeah, exactly. It's a host-guest complex. So if you drop iodine on a powder and it turns black, you know you have a starch. But now you have a new problem. Is it flour or is it cornstarch?
They both turn black.
They do. This is where observation skills come in. Flour is usually described as off-white. It has a creamy, slightly yellowish tint, not stark white. Cornstarch, on the other hand, is pure, brilliant white, like printer paper.
And the reaction looks a little different, too. The notes mention bubble shapes for flour.
Yes, because flour contains gluten, it reacts with the water in the iodine solution differently. It tends to clump up and get gooey. The iodine drops form these little bubble shapes or distinct clumps.
Whereas cornstarch...
Cornstarch absorbs the iodine smoothly. It turns black, but it doesn't get that gummy, gluteny texture.
And if you mix them with just water...
Flour makes the water cloudy and clumpy, like bad gravy. Cornstarch gives us one of the most fun phenomena in physics. Have you ever made oobleck?
The stuff that's solid when you punch it and a liquid when you pour it.
That's the one. It's a non-Newtonian fluid. If you mix the powder with a little water, and it gets hard when you apply force, but flows when you relax,
Yeah.
it is definitively cornstarch.
I love that defying physics is a valid forensic test. Suspects A, your alibi is weak, but your pantry defies Newton's laws.
It's a very tactile test. You poke it with a scouring rod. If it fights back, it's cornstarch.
Okay, moving on to the fizzers, the powders that react to acid.
Right. We're using hydrochloric acid or vinegar here. If it fizzes, it means gas is being released, usually carbon dioxide.
And our main contenders here are baking soda and limestone.
Let's look at baking soda first.
Yeah.
Sodium bicarbonate. This is the classic volcano experiment. You drop acid on it, and it fizzes aggressively. It wants to release that gas.
But limestone fizzes too.
It does. Calcium carbonate. It also releases carbon dioxide when with acid. But how do we tell them apart if they both fizz?
Solubility.
Correct. Baking soda is soluble. It dissolves in water. It disappears into the solution. Limestone is a rock. Calcium carbonate does not dissolve in water easily. It just makes a sandy, gritty mess at the bottom.
There was also a note about iodine and limestone, a color change.
Yeah, this is a weird specific reaction mentioned in the rules. Limestone turns a sort of peanut butter or mustard color when you add iodine.
Yeah.
It doesn't turn black like starch, but it doesn't stay orange like salt. It has this distinct earthy hue change.
Peanut butter limestone, I'll remember that. And finally, the construction materials, plaster of Paris and sand.
Plaster of Paris is gypsum, specifically calcium sulfate hemihydrate. The hemihydrate means it's partially dehydrated. It's a fine grayish powder.
And the dead giveaway here is water.
If you mix it with water, it undergoes an exothermic reaction and rehydrates back into gypsum rock. It hardens into a solid block.
Which makes sense, since we use it for casts. And then there is sand, silicon dioxide.
Irregular grains, often multicolored or beige. It doesn't dissolve. It doesn't fizz.
The sources mention a slight bad odor when you mix it with iodine.
That's a quirky observation from the guides, likely due to impurities in the sand, like organic matter or sea spray residue, reacting slightly.
The main implication for sand isn't chemical, though. It's locational.
Right. Sand is trace evidence. It tells the story of where the suspect has been. The beach, a playground. Or, the notes mention, maybe they work in tech.
Silicon is the base for computer chips, so finding silicon dioxide might implicate a software engineer.
Precisely. Context is king. You connect the powder to the person.
All right, we've dusted for powders. Let's pour over the liquids. We touched on wafting. But how do we identify clear liquids that all look like water?
Smell is your primary tool, followed by pH. You're building a decision tree in your head.
First up, hydrogen peroxide.
Visually, it looks like water. Smell-wise, it has a faint, sharp, almost metallic odor. But the visual test is the iodine again.
Iodine seems to be the MVP of this kit,
It's very versatile. If you mix hydrogen peroxide with iodine, it bubbles.
like the baking soda with acid.
Visually similar, but the chemistry is totally different. This isn't an acid-base reaction. This is catalytic decomposition.
Hmm.
The iodine acts as a catalyst. It speeds up the natural breakdown of the hydrogen peroxide.
Break down into what?
Water and oxygen gas, those bubbles you see, that is pure oxygen escaping the liquid. It can even get warm because it's exothermic.
And the implication.
It's a common household item, used for disinfecting wounds. Maybe the suspect scraped their knee. It's also used in gardening to treat root rot.
Next up, vinegar.
Acetic acid, strong, sour smell.
And the pH?
Acidic, usually around 2 or 3. It'll turn litmus paper red immediately. If you add iodine, it doesn't bubble. It just turns a brownish color.
Then we have the control. Water.
H2O, neutral pH of 7. No smell, no reaction.
In a crime scene, finding water could implicate a suspect who visited a pool or a beach, right?
Exactly.
Yeah.
Or simply, why is there a puddle here? Was there ice that melted? Was something cleaned up?
Rubbing alcohol.
Isopropyl alcohol, distinct medicinal smell. It has a cooling effect on the skin because it evaporates so fast. Cleaning sticky residue, removing ink stains. If you find it, you might be looking for someone who is trying to clean up evidence.
And finally, ammonia.
The smell is overpowering. But chemically, the key identifier is the pH. It is the only strong base in the standard kit, pH 11 to 12, implicated in heavy-duty cleaning products or fertilizers.
Let's move to something a bit more colorful. The ink race. Paper chromatography.
This bridges art and science. You have a mixture, like black ink. But black ink isn't just one thing. It's a cocktail of pigments blended to look black. We want to separate them to see the fingerprint of that pen.
And we do that by making them race up a piece of paper.
That's a great analogy. You have a stationary phase, which is the paper, and a mobile phase, which is the solvent, like water or alcohol. You put a dot of ink on the paper, dip the bottom edge in water, and the water climbs up the paper.
How does water climb up? Gravity should push it down.
Capillary action. It's a mix of cohesion water molecules sticking to each other and adhesion water sticking to the paper fibers. The water pulls itself up through the microscopic gaps.
Okay, so the water is moving up like an elevator, and it drags the ink molecules with it.
Yes, but the ink molecules don't all move at the same speed. The sources use this great analogy. Water lovers versus paper huggers.
I love that. Break that down for us.
It comes down to polarity. Water is very polar. Some pigment molecules are also polar. They are water lovers. They dissolve easily in the water and want to stay with it. So as the water zooms up the paper, these pigments ride the wave and travel far.
And the paper huggers.
They're less polar. They are more attracted to the paper fibers than to the water. They get stuck. They travel slowly and get left behind near the starting line.
So at the end of the race, you have a streak of colors. Maybe blue is at the top because it loves water, and red is at the bottom because it loves paper.
Exactly. And that pattern is unique to that specific pen brand. A Bic pen looks different from a Sharpie.
But to make it scientific, we need a number, the RF value.
The retention factor.
Yeah.
You measure how far the specific color traveled, the slew distance, and you divide it by how far the water traveled, the solvent front.
Distance of color divided by distance of water.
Right. And because the color can never travel further than the water carrying it, the number is always less than 1.
So if the water went 10 centimeters and the yellow pigment went 9 centimeters.
9 divided by 10 is 0.9. That's a high RF. That yellow pigment is a major water lover.
And if the red only went 2 centimeters, that's an RF of 0.2, a paper hugger. One practical tip the sources mentioned, use a pencil to draw your starting line. Why?
Because graphite is not soluble in water. It stays put. If you used a pen to draw the starting line, the line itself would start moving and mixing with your evidence.
Always use a pencil in the lab. Now, from ink trails to finger trails, let's talk biometrics. Fingerprints.
The golden rule of forensics. No two prints are alike, not even identical twins, because prints are formed by random friction pressures in the womb.
So it's nature and environment.
Exactly. We categorize them into 3 main families: arches, loops, and whorls. But first we need to identify a landmark called the delta.
Named after the Greek letter, which looks like a triangle.
Right. In a fingerprint, it's a triangular area where the ridges flow in from 3 different directions and meet. It's the traffic circle of the fingerprint. Finding the deltas is the key.
Let's look at arches first. They are the rarest, right?
Only about 5% of the population have them, and they have 0 deltas. The ridges enter from one side, rise up in the middle like a hill, and exit the other side.
There are 2 subtypes, plain and tented.
Plain is like a gentle rolling hill. Tented is like a sharp camping tent. It looks spiky.
Next, loops. These are the most common.
60 to 70% of people have loops. A loop has exactly 1 delta. The ridges enter, loop around like a hairpin turn, and exit the same side they came in from.
This is where it gets anatomical. Radial loops and ulnar loops. This connects to the bones in your arm.
You have 2 bones in your forearm, the radius on the thumb side and the ulna on the pinky side.
Okay, so if I'm looking at a print,
First, you need to know which hand it came from. If it's the right hand and the loop opens toward the thumb, the radius, it's a radial loop. If it opens toward the pinky, the ulna, it's an ulnar loop.
and 94% of loops are ulnar?
Yes, so if you see a radial loop flowing toward the thumb, that's a very distinctive feature.
Finally, the whorls, the swirly ones.
Whorls have 2 or more deltas. The ridges form a complete circle or a spiral in the middle. We use the imaginary line test to tell the types apart. You find the 2 deltas and draw a straight line connecting them.
Okay.
If that line cuts through the spiral ridges in the center, it's a plain whorl. It hits the bullseye. If it misses the central spiral, it's a central pocket loop,
Then there's the double loop.
the yin-yang. 2 separate loops swirling around each other to form an S shape. And the accidental, which is a mess, it doesn't follow the rules. Very rare.
Now, finding these prints isn't always easy. We have latent, patent, and plastic prints.
Plastic is a 3D impression, like a finger pressed into putty. Patent is visible, like blood or ink on a table.
But latent prints are the invisible ones, left by sweat and oils.
To see them, we use chemistry. Dusting with black or white powder is the classic move for smooth surfaces. But for porous surfaces like paper, we use 9-hydrin.
That reacts with amino acids?
Yes, and it turns a bright purple color called Ruhemann's purple. Then there is superglue fuming. The chemical name is cyanoacrylate. You heat up liquid superglue, it turns into a vapor.
And the vapor is attracted to the oils in the fingerprint.
It hardens right on the ridges. It forms a hard, white, crusty residue. Freezes the print in plastic permanently.
So once we have the print, we match it using the ACV method, analysis, comparison, verification.
Analysis is asking if the print is even good enough. Comparison is looking at the minutiae, the tiny details like ridge endings or bifurcations, side by side with the suspect's print.
And verification is giving it to another expert blindly.
Exactly, to prevent bias.
Speaking of things that need to match, let's talk about blood typing. A mismatch in fingerprints means catching the wrong guy, but a mismatch in blood transfusion means the patient dies.
High stakes. Blood contains antigens. Think of them as little flags sticking out of your red blood cells.
If you have A flags, you are type AB flags, type B. Both, you're AB. No flags, you're type O.
The O basically stands for 0 antigens. And there's a third flag, the RH factor. If you have it, you're positive. If not, negative.
So in the lab, we use the clump test or agglutination. We drop anti-serums onto the mystery blood. Anti-A antibodies are like flag hunters programmed to attack A flags.
If the blood has A flags, the antibodies latch on and tie the cells together. The blood clumps up, that's agglutination. So clumping in anti-A means it is type A.
And if it stays smooth, no A antigens. Same for B and RH. There is also a control well that just has saline.
It should never clump. If it does, your test is broken or contaminated.
Why does this matter for transfusions? Your body produces antibodies against whatever flags you don't have.
If you are type A, you don't have B flags. Your immune system builds anti-B defense systems. If you get type B blood, your army attacks and clumps the blood inside your veins,
which causes hemolysis, where the cells burst. Very deadly.
This leads to the universal donor, O negative. It has no antigens. It's in stealth mode. The recipient's immune system doesn't see any enemy flags.
And the universal recipient is AB positive.
They have all the flags. Their body recognizes everything as self.
The rule is you can donate if you have the same antigens or fewer. Okay, we have analyzed all this data. Now comes the analysis, putting it all together to catch the bad guy.
You switch from scientist to lawyer. You build a case. The sources suggest a tally system. You list your suspects and put a check mark for every match.
But we have to weigh the evidence. DNA and fingerprints are individual characteristics.
They point to one specific person. Strong evidence. But if we identified flour and suspect B is a baker, that's a class characteristic. Anyone can buy flour.
Let's talk about motive, the Dubai chocolate example.
If the crime involves stolen Dubai chocolate and suspect A likes Dubai chocolate, that is a strong motive. If suspect B just likes sweets, That's a weak motive.
And if suspect C is allergic to chocolate, that is no motive. It clears them.
The analysis section needs to explain the who and the why. Connect the dots.
And there's the other section for outliers, like mystery DNA at the scene.
You have to note that. Or if the suspect has an innocent reason for being there, like they were cooking in the kitchen earlier.
We have covered a massive amount of ground, from salt crystals to antibodies to legal logic. What I love is that Sherlock Holmes shows how forensic science is just the application of basic scientific principles.
It's understanding that starch traps iodine and water climbs paper.
Before we go, a thought to chew on. The data is objective. The powder fizzes or it doesn't.
Objective fact.
But the story we tell involves interpretation. If you find baking soda on a suspect and you know they are a baker, you see evidence. But baking soda is also used for cleaning teeth.
Confirmation bias.
Exactly. The science gives us the dots, but we draw the lines between them.
And that is why we have the verification step.
Something to think about next time you make oobleck. Thanks for joining us on the deep dive.
Keep analyzing.
See you next time.